All right.
So module 2 on SystemVerilog fundamentals, and so we're not going to go through every detail of RTL since we have covered a lot already. The RTL, advanced digital. So here is just basically showing the main syntax and the fundamental differences between Verilog and SystemVerilog to help you later with your project and also for the test. On this course, writing RTL, SystemVerilog. Okay. So quite a lot of things here that we're going to cover. Advantages, why we use SystemVerilog, the different styles. Okay, the different styles, the structures here, like the C-type structure. So a bit of the different fundamental concepts in SystemVerilog. I believe nobody is working in front end. Ada yang buat front end design tak tadi? Macam tak kira. Oh, you do front end design. You use SystemVerilog or Verilog tadi? Hard IP. Circuit design.
Also
Front end design using RTL or oh, just circuit design. Okay, yes. Front end circuit design. That's different. Kalau front end RTL design lain kita buat analog circuit design. Analog circuit design. So there was more the transistor level design, right? Transistor level different than this. Anybody doing RTL design? Front end RTL? Tak ada. Atau you doing RTL design? Using Verilog, SystemVerilog? Verilog. Or still using Verilog RTL? Okay. Verification. You design or verification? Design. If it's design, mainly, as far as I know, mainly still using Verilog RTL. But if you're in verification, test bench, ada yang buat verification, test bench using SystemVerilog? Tak ada. Kalau verification, normally the industry they use SystemVerilog for verification. Okay, it's more. You can see it's more convenient. It's more convenient. You have more things that you can do actually with SystemVerilog. But anyway, we all learn this language. Just in case later you want to go into RTL design verification, and you want to change your area of expertise, you change your job description. You have experience with SystemVerilog. Okay, so why SystemVerilog? That's the first question. We already have Verilog. Okay, why designers need to go to SystemVerilog? So the issue is designs are getting very large and more complex. Okay, the CPU is getting bigger, many core, multi-core to many core, hundreds of cores, hardware accelerators getting much more complex. Test benches are growing because the design is big. The test bench also getting bigger. User also demand for tools that is more flexible and more maybe user friendly. Okay, compared to Verilog, very strict language. Okay, so you make the language more flexible. Okay, Verilog is not that flexible in my opinion. System level modeling. Okay, currently we talk about SOC. SOC system level modeling. We need a new design approach. So Verilog RTL, the classical Verilog, maybe not so suitable anymore. Okay, although I would say the industry is still using it. Okay. So SB provides a new design constructs relevant to the RTL system. Okay, so something interesting to know is Verilog was created in 1984. How many years ago is that? So 1984, 40 years, eh? 40 years. Okay, so Verilog, 1984, they came up with the standard in 1995. So the first Verilog 95 standard, you have the module parameters, function task is there, always add there, assign is there. So these are classical. Module parameter function always assigned is a classical. Verilog that is also being used, in the modern, you can say the current system Verilog as well. The others like monitor we still use, right? These are from the original Verilog standard. Okay, the while, if, else, begin, end, repeat, okay, time scale. Okay, so these are classical Verilog 95. And then in 2001 they added some more syntax. They added more the generate. So Verilog 2001 support the generate, local param, constant functions. The others, at least for me, not need to use multi-dimensional array. 2D array. 2D array, Verilog 95 doesn't support for multi-dimensional array. Sign types. Okay, so Verilog 2001, and then Verilog 2005 standard, they added a little bit more. Begin is also quite widely used. The others, I'm not so familiar. Okay, begin here. Okay, and then people will be using the Verilog 2005, so currently, so if you save a .p by default, it's Verilog 2005. Okay, it's our so Verilog 2005 is subset, so it's a subset of the Verilog 2005. Okay, next, they then created the SystemVerilog, so they don't call it the Verilog 2009, 2012. Now it's a .sv. Okay, .sv is a different file extension to support much more syntax. So I think that's the reason, because they want to support much more syntax, so it's not very long anymore. Dia dah jadi unrecognizable. You know, it's especially in verification. Okay, is you know, the structure, macam the directive function call, initiating all these in two-state data types, the shifting methods. Okay, so these are only supported in the SystemVerilog, okay, in the design and the verification constructs. So they added quite significant number of syntax, and they call it a new language. Okay, with a new extension. Okay, we are not going to go each one. We are going to go through each one of those, but we're going to go through the important ones that's what we're going to use in our class. Okay, so advantage of SystemVerilog as compared to Verilog is that it's more concise, more expressive, friendly RTL notation, accurate modeling, okay, consistent behavior across all tools, logic styles that are readable, easier to maintain, more functionality with less code and less errors, procedural block enhancements. The procedural block enhancements here using the new always syntax. In Verilog it's always net. So here your procedural block in SystemVerilog, okay, mainly that's the main thing is always FF. Okay, there is always FF, always call. Okay, so previously, if you in Verilog, if you remember, if you had the always procedural block for combinational or not combinational, see, for sequential and combinational, both is always always add. Okay, and then sensitivity list. So here you differentiate between combinational and sequential procedural block. Okay, they are different. Yeah, I like this one. It's more readable, and you can see all this combination sequential. You can see. Okay, kalau dia tak nampak. More efficient state machine. Okay, interface construct. Interface is something we're going to discuss in detail tomorrow. Okay, I think not in this part. So the interface construct is you know, it's really also a good concept. Okay. In SystemVerilog, and then very useful for complex design. Okay, simplify the communication between blocks. So if you have hundreds of, let's say, memory controller, right? Memory controller, you have 100 signals. Okay, then you write enable 1, enable 2, and then you have a chip enable banyak. Okay, a lot of signals. You can combine all these signals together into one interface. So this is a nice feature that you don't have in Verilog. So in Verilog, it's messy. So much. Banyak signal. A lot of signals, so here it makes everything more organized. So this is a nice feature. This is a nice feature. Data type, okay. The other nice feature is the data type. The data type. But this is the list that they have in the book. Right. Okay, so this is one of the main features, okay, of SystemVerilog, and we don't use wire and mesh anymore. Okay, so in your coding data, we don't use wire and mesh. Okay, we use logic. Okay, so kalau in Verilog, we use a wire, mesh. Over there, we use logic. Okay, output mesh, output logic. What's the difference between wire mesh and logic? So first of all, logic is a 4-state data type. right? You can take the value of 0, 1, high impedance Z, or the low cat X, right? But the main thing here is that the logic can be driven in both the always initial and also assign. So you don't have to worry about, okay, you like instantiate this block, and then the rest you don't worry about. Because before this, if you have the always block, you have to use the rest, right? If it's an output of the always block, you have to use rest. Okay, kalau tak, you have compilation error. But in this case, if you use inside the always block, or even outside the assign statement, you just use this is nice feature. So you don't get confused. Okay? Okay, so later we see more example of that one. Okay, so something interesting to note is that logic is a 4-state data type. You can take ZX, but there are data types that takes only a value of 0, 1. Okay, they are yang biasa kita guna integer lah. Okay, if I so integer is a 52-bit signed integer, they can only take the value of 0 and 1. Other than that, you can also use bit. Okay, bit is a user-defined vector size. Just that one bit as well, actually, but it's only taking 0 and 1. Short means 16-bit, long means 64, and then the byte is 2-bit sizable as given. Okay, they're all synthesizable. Restrict only without XYZ. Okay, so in SystemVerilog, use IND, just like the C style coding. In the Verilog, you remember integer I, right? Integer I, integer J. So in here is more intuitive, right? If you write C program, people use it, right? So now they change it, and it's more, it's more concise, and it's it's better. Integer I is strange, right? Integer I is like a full name. Okay. So now use it, right? Okay, this is another interesting one. Okay, if you use state machine, use enum instead of parameter. So in Verilog before, maybe you use parameter. In the parameter, normally we define like this. There might be different way. We define each state needs to assign a certain number of integer, right? With the number S00, S11. Okay, but in SystemVerilog, we don't need to use parameter anymore. We can because it's a subset number. We can do like this, no error, but it's more preferable to use the SystemVerilog syntax, which is enum. So for example, up here, enum and sub is a state. You can say it's a state. Okay. Of course, here is like the present state, let's say present state or next state. Okay. Case, present state of code. Okay, so these are the states. Okay, so enum enumerate the states. Okay. Another interesting feature that is very useful in SystemVerilog is you can just use the apostrophe for unsized circles. So for example, we have logic 12-bit bus, data bus, initial begin, data bus equals to apostrophe 0. Okay, which means that we want all the bits in the data bus is 12-bit, right? So it's a 12-bit. So here is this is in Verilog. In Verilog, you have to specify this 12. You have to specify this 12. Okay. If you do like this, probably you get compilation error, synthesis error. Okay, in Verilog, right? In Verilog. So you need to save .sv, then only you can use this. Okay. Why is it interesting? Let's say, for example, I change my data bus to 32-bit. Okay. I change my data bus to 32-bit. Do I need to change anything in my coding here? No need. Okay. But in Verilog, if I change data bus to 32-bit, I need to change this to 32, right? Manually, one by one, going to come. 32, all the way. Okay? I change 32-bit there, run, error. Okay? Because I have, well, maybe not error, maybe the only 12-bit I change. I set the X on 0. The remaining bits, maybe random. Okay? Or maybe it gives error. Alright? So in SystemVerilog, we say, alright, we change the bit 32, doesn't matter. Alright, doesn't matter, it will initialize correctly. Alright, so that's another interesting feature. So of course, I guess it creates some kind of maybe your Verilog is maybe a more stricter language. It gives a more flexibility, right? It gives a more flexibility, but the designer don't really have control. So maybe some designer, or maybe why the industry are still using RTL, Verilog RTL. Okay, because you can actually control here. You can control. Some people like to control this number. Okay, they want to control it. Don't have too much flexibility. All right, so it might be a good thing. I don't know. But in any case, SystemVerilog it does everything flexible. So you don't have to worry about that number. Okay, type def. Type def is also interesting. Type def allows the user to create your own data type definition. So, for example, here, you create a type ubyte. Okay. You create a type, namanya ubyte. The ubyte is a type byte unsigned. So new data type ubyte is created of type byte unsigned. So byte unsigned, so ubyte AB. So A here is byte unsigned. So instead of you put in the byte unsigned A, okay, byte unsigned A, you put ubyte A. Okay, byte unsigned B, you put ubyte B. So it's more concise, right? You type this kali here. Okay, so you tak payah, you don't have to put byte unsigned A, B, banyak-banyak. Dan kat bawah lagi, okay, maybe some other variables kat bawah you nak byte unsigned juga, so you just do byte. Okay. Okay, Boolean type def enum. Okay, so you can also have a type def enum false true Boolean. Jadi dia punya new data type is called Boolean. Okay, Boolean ready. Okay, so ready can be false. New data Boolean of type length. Okay, let's look at the structure. Structure is more like a C style. I think we also have C. Structure is C, right? If I'm mistaken, in C program. You can also have a structure. So structure is like a class and object in C, right? So for example here, you can think of it as a class instruction. All right. So you have a class instruction, structure instruction, and inside the instruction you have your variables, right? You have your variables for this particular class of structures. So inside the instruction you have the output, integer A, B, and also the access. Okay, so to access the data, let's say you want to write the output here. So you go instruction dot output. So instruction dot output. You bit binary 0, 1, just possibly 0. 0 or 2 bit binary 0. Okay, so I think the advantage here is that you can see that the output is part of the instruction structure. That's the thing. Okay, if you don't have this structure, your name will be instruction underscore output. In Verilog, in Verilog maybe you call it instruction underscore output, very panjang. Right? If you put output sahaja, is it part of instruction or not, kita tak tahu. So in SystemVerilog, you do instruction dot output. So inside the instruction you have many things. You have the address, you have output, AB. So it makes it more readable and easier to trace, I would say, right? This output is coming from the instruction structure. Okay. Okay, so then you can also create the object. Okay, you can create an object, but need to define the type def first. Okay, macam tadi dia tak ada type def. Sini dia tak ada type def. But remember the type def. Type def you can create, you can say like an object lah, like variable object. So bila you type def something, then it becomes you byte something. So then you can do a type def struct. Type def struct. Okay, so bila you buat type def struct instruction, so instruction 1, instruction 2 will be, you can think of it as your objects, right? So instruction 1 is your object, and then to access the data macam mana? So inside the type def struct we have the output underscore D output. we have int AB and logic 34-bit address instruction T. So output underscore T is a user-defined data type. For example, type def int unsigned. I think this should be unsigned integer. Nanti is correct. Okay, so let's say it's int unsigned. So it's an unsigned integer, right? The 32-bit unsigned output T. So output here is the unsigned 32-bit unsigned integer. Okay. So how to reset instruction 1 address is 0? Okay. So what is the syntax? Okay. So what do you think it will be? How to reset instruction 1 consists of all this, and I want to set my address to 0. So how do I set my instruction 1 address to 0? Address actually, not output. You will not set the address to 0, not output to 0. Very simple one. Okay, just to see if you are next to the last, so the answer should be so here you can say instruction 1 dot ADR equals to 0. Okay, ataupun boleh buat 0 lah. You put the bit number depan ni, it's a Verilog standard. Tapi remember, Verilog is a subset of SystemVerilog di dalam. Ini you boleh guna all the Verilog syntax di sini. It's a subset. Jadi yang tadi SystemVerilog saja. Okay, but we can also do ni 24 ya. 24-bit binary. 24. Boleh juga kita 24-bit binary 0. Okay. Save.sv, I think you can write. Okay, no issue. Tambah 1. Oh. Ya. Sebab yang apostrophe 1 tu, it's not 1 tau. It's not 0001. Apostrophe 1 tu maknanya all the bits, let's go selected. All the bits bukan. Kalau jadi 1, you buat tambah 1, right? Dia akan jadi 00001 lah. Kalau integer data bus, dia nak set semua 1, kalau integer dia tunjuk. Okay, so kita tukar integer data bus. Integer data bus nak ada apostrophe ke tak? Apostrophe 1 dia jadi 1 lah. Bukan. Kalau integer, I think dia akan jadi satu semua juga. Sebab you buat apostrophe. When you put apostrophe, it means that every bit 1. Not 100% sure, tapi my opinion je. Because kalau you nak 1, you buat apostrophe. Okay, kalau you buat apostrophe, dia akan jadi integer data bus equals 1, which is 00001. Kalau you letak apostrophe, it means that you want each bit, setiap bit tu 1. Make sense? Tapi kena check, kena run. You can try run. But integer normally kita guna, you don't play with individual bits, right? Kalau integer kan, integer I plus 1 plus 2. So kalau you nak play with individual bits, you normally use logic lah, wire rest lah, kan? wire rash kalau macam you have some controlling individual bits, somebody use logic. Tapi kalau you nak as a variable yang bukan output, input output. Kalau input output ke system, normally you use logic lah, kan? Wire rash or logic. Tapi if it's an internal control, okay, for loop lah. For loop is an internal control, then you use integer lah. So integer normally we don't do the apostrophe lah, kan? Kalau integer terus ditambah equals to 1, which is 00001. So okay, dari sana. Okay. Okay, so yang ini jawapan dia boleh macam ni, tapi this one is not recommended. Not recommended for SystemVerilog. So for SystemVerilog, you just want to go apostrophe 0 ataupun you can put 0 pun okay. Saya rasa kalau you put 0, macam semua 0 00000. Okay. If you want to initialize to FFF, ini berapa bit? 34 bit, you ada 6, you have 6. So if you want to initialize to FF, you put apostrophe 1, right? So akan jadi 1 sebagainya. 6 kali F kan? Jadi 6 kali F kan? FFF, FFF, 64 bit, 24 bit of the address. Okay? Okay, let's analyze SystemVerilog punya coding. Okay, yang atas Verilog, and the below one is SystemVerilog. Okay, and on the right there is the block diagram for the SystemVerilog. Okay, block diagram for SystemVerilog. Okay, so what it's doing? We have a top circuit. Let's look at the top one first. We have a top circuit here. The top circuit, there is input A, output is B. Okay, Verilog, output is B. And then the instantiate inverter, clock instance with AB connected to the inverter, and this one will give error. Why? Because the variable cannot be connected to the output port. The error is because rash here. You are not allowed to put rash there because the instantiation there is not inside the whole block. Okay, so Verilog will give error, and it's confusing, right? But in a way, it is a restriction. In a way, macam some people like it, macam okay, you can really control. Kalau nak instantiate, jangan guna rash. Right? You can control it. Okay, but in SystemVerilog, okay, SystemVerilog you panggil logic kat sini, no error. Okay, kat sini you boleh buat ni, you can remove this logic, no issue. You can remove this logic, it still work. But even if you put logic here, it will still work. Okay, no error. But in Verilog, you must remove rash. Okay, in Verilog you must remove rash. Even though kalau tengok B ni dia rash B ni is inside the old block. Okay, and then the inverter here is wrong. Inverter here because your output is kena rash, right? Because you are the old block. So now it's confusing. In SystemVerilog, you can put logic here, becomes logic. Here put jadi logic, no error. Okay, so dia remove all this confusion about bila nak guna wire, when you use a wire, when you use a rash, you need the rash or not. So everything is logic. So you can say everything is logic. Okay, you nak instantiate, you nak guna assign, inside always block, outside always block. You can just use logic, doesn't matter. Okay, you have this flexibility. Okay, but some people don't like this flexibility. I believe so. But here, if you do like this, error. You need rash here. Okay, you have to remove rash. Okay, so let's try to draw the block diagram. Okay, maybe a little bit of revision on your RTL. Okay. So what we have the top module instantiating two inverter. So top module is two inverter. We have the logic here, logic A, assigned in1 equals to 1, and in1 is a logic, is input logic. Okay, input pun boleh logic juga, input. Okay, output logic out, so also okay. Okay, and then we have two inverter, and in1 is connected to the atas tu. Okay, and then back to the logic gate, which is the internal signal of the top module, and then we have the second inverter. Okay. Nah, dah dapat dah. Alright. Okay, yeah, just what you call it, revision, macam dia punya apa, RTL, kalau dia look at a lot of RTL for this meeting. So, okay, so how is the inverter connected? How is the inverter connected? Ada siapa buat marker tak? Tak ada. Oh ada? So baik. Kalau lain mana? Dia standard colour dia hitam. Tak boleh. Ini one marker. Okay. So let's see. So kita ada top module. Kurang jelas. Kita akan lihat ni. This was the top module and on the top top left, right? Okay, and then kita ada dua inverter. Then this one dia ada block dia, right? Okay, and then this is the inverter INT. Okay, and the bracket is going to put instant one. Okay, so the instant one inverter, and then they have the instant two inverter. Okay, and then we have the internal signal. So for inverter instant one is the input is in one. Okay, and then the output is A. So you have the A here, and then you have the in one. Okay, in the top module. So tapi yang ni the input. In one is the input to the top module, and then you have the it's up. Okay, but internally, this one internally is in one and out one. So in one, out one, in one, out one. Okay. So okay, so internally is in one, out one. But this in one is connected to the in one of the top module. Okay, connected to the top module. Out one is connected to the out of the top. Okay, right. Any questions? I think straightforward, right?
Yes. The function of the budget because the module
Okay, I think this is wrong. This is an error in the book here. It should be R1 because R1 is undefined. Kan, R1 tadi resi kan? R1 is up there. But R1 is not defined here. Okay, in one, R1 is supposed to be this one. Okay, So yang ni kena buat awal. And else you have an error, outone is not defined. Kan? Okay, this one supposed to be out. If it's outward, it doesn't make sense. Okay? Because outward is this module. It doesn't make sense. Unless you define logic outward. Here, logic outward, but then it's going to what? Then you have to say outward equals to out. Okay. Any other questions? Okay. The other thing is a little bit confusing here. I mean, it's not normal. Not so normal. Normally, input we don't give logic to the input. Okay, only the output that we give logic. But here they purposely put logic for in-one. Because they want to assign the input to one. Okay, can you assign the value to the input or not? That's a bit strange that you assign the value to the input, right? Because the in-one is supposed to be coming from outside. Okay, in-one coming from outside, but you are forcing this to be equal to 1. Assign in-one equals to 1. That's a bit strange. Okay, a bit strange there. It's not normal. I think just this example. Okay, I'm going to force this wire to be equal to 1. But the input logic in 1 on the module top. What happens if somebody wants to use the top module? I put a 0 here. I give 0 to my input. What happens? So then you have a problem. It's a contention because in the top module you are forcing this to be equal to 1, but the user who is using this I want to give 0 in the simulation. Okay, so maybe there's some error or something. But here I think it's not normal. I think they just want to say that you can put logic for the input, then you can assign a constant value to your input. Okay, I think in Verilog cannot do this. In Verilog you cannot do input rest. Input rest ada input wire, wire boleh tapi input rest tak boleh. But I don't think they do this in Verilog. A is an internal net declares logic. A is an internal logic, is 1 is last. Is logic. Okay? Okay, can we move on? Any questions? Can we move on? Okay, let's move on to the next one. Operator president SystemVerilog is should be the same as Verilog. Should be the same. Okay. Just that this triple shift here, one of them is logical and arithmetic shift, right? The shifted there, I think it's only SystemVerilog. Yeah, so kalau tengok the Verilog identify they support double shift. Okay, might be logical shift. I need to check. Tapi only one kind of shift. But if you do a triple shift, okay, triple shift is only supported in SystemVerilog. Triple shift tak boleh in Verilog yet. So what's the difference between a triple shift and a double shift? I don't have my phone with me. Kalau tak boleh Google sekejap. Okay, aku tak ingat. Okay. pun kat belakang. But not important, not important. I mean, there's a difference, right? One is logical and arithmetic lah. Okay, how it works, the detail, you can find, you can read yourself the detail. But it's a different kind of sheet, and if not mistaken, Verilog don't support the triple sheet. Okay, so in SystemVerilog they support this triple sheet. Okay, that's one. But other than that, the precision is the same. Okay, so if you have this one, y equals to something there and z equals something there, which one you will do first? Dengan shift dulu ke, dengan multiply dulu, this one first or this one first? So you have to get the precedence. Okay? So cuba buat dia bracket, which one is doing first? According to the table. Okay. Personally, I will put myself. Actually, I'm not like this. Okay, kan? So I will put bracket myself. If not, if you put bracket, then it's override the precedent. Let's say I put bracket here. Okay, then I will do this one first, right? If I put bracket. So I will put bracket lah. Tapi this one is just for just to understand the precedence. Okay, so which one will do first? Okay, so you will of course do the multiply first. You do multiply first, and then you will shift, and then baru dia tengok yang ini. Okay, yang N dengan ni is not really clear which one goes first. If you don't see the table, you will not know probably. Okay, you have the table in front of you. But if you have to guess, I will guess this one go first. This one go first, right? Because this one is more commonly used as compared to this one. So tengok here, N goes first. Okay. Okay, what about this one? So this one, of course, the divide will go first. Okay, divide, and then you do plus dulu, right? Minus dulu, plus dengan minus mana dulu? Sama. Kiri, plus dulu. Plus dulu. I rasa plus dulu. Kalau plus dengan minus, buat plus dulu. Okay? So dia left. Yang presiden dekat belah kiri macam multiply dengan divide. Multiply divide, I think they will multiply first. I might be wrong, tapi I think so. Betul tak? I think so. Dia akan buat multiply dulu. Okay. So then we have y. Okay, so we do this one first. Okay. Then like this. Last kali baru yang nak. Okay. This one maybe. And this one. Okay. And then we have the Z. Okay. So I will do the divide first. The last next. Minus next, pasti baru the shift is the last one. Okay. Okay, so that. Okay, right. Okay, so just be aware there is a non-synthesizable operators in SystemVerilog. So A++, I++. Plus equal is only supported in test bench only. Okay, not reused in your design. Okay. Port connections, methods for port connections. So the dot star here, is it supported in Verilog RTF or not? Macam support I'm not sure. The dot star. I will use Verilog for some time. Yeah, I always use SystemVerilog. So in SystemVerilog, I like to use the dot star. Okay, kena tengok tak dot star dalam Verilog? Tak pernah pakai dot star? Yes. So later we see the example for dot star, alright? But the normal way is okay. So So flip-flop is the name of the module, right? Name of the module, name of the instance. Dot clock is this clock here is the port for this FF, right? Yang ni yang dia punya. Okay, this clock here refers to this clock, right? So in the bracket is this one. Dot D here is the dot D of this, and then D here is connected to here, and then dot Q is here, and then Q here. Okay. And then number two is dot D dot Q. So this one because it's the same name, because it's the same name, so dot clock automatically will be connected to the clock here. Okay, this B will be connected to this B, and this Q connected to this Q. Okay, and then the dot star, if you have the same name, clock DQ, the same name, FF report you have clock DQ. Okay, then you can do dot star, then you automatically will match the name. So the name here is CLK dia akan match this. Okay, dengan syarat, with the condition that the name of the top module and the name of the FF, the instantiating module, is the same. Yeah, there are a lot of cases in Malaysia. So again, I can have my phone, but I'm going to use it. I'm not 100% sure. Okay. But if not mistaken, it is tadi kita check. I think it's case sensitive, right? Is it? Anybody knows? Dia is case sensitive. I think it's case sensitive. Apa yang kita check? Itu good question. Okay.
Pasal itu dia takkan collect sendiri.
Oh, the last one. Okay, the last one is the dot star. So dia akan match yang match saja. So for example FF ni dia ada clock DQ, clock linear. This clock here is for the port of this guy. Okay, and then there ada DQ. So the DQ will be connected by the dot star yang DQ ni, and then the clock tu dia akan sambung ke clock ni. So you can mix lah. Macam yang so the dot star will connect the one in the same lane, and then yang customer different lane will be connected manually. Manually I mean, you know, explicitly connected. Okay. Okay. So this is a nice feature. I think it's a very nice feature of SystemVerilog. So previously in Verilog you are always happy. You don't have this always call. You don't have the always call. Okay. You always saja, and then you have the sensitivity list, right? Always at, and then you have the list. Okay. And then for the flip side also in Verilog you have the always no FF here, and then you have the this lah. Okay. Okay, if not here on the set. So in SystemVerilog is a nice feature. No need sensitivity list. No need. They put saja automatically because obviously you know sensitivity list. For example, here you want to put set. Anything that changes. Yeah. So when cell ataupun B ataupun A. So normally you akan buat always add cell AB. Okay. Right. Always add cell AB. Anytime the cell AB change value, then we evaluate, right? So in this case, they automatically will do the list for you. Okay. So you don't need to put that. That's a nice feature. Okay. And then the flip flop. The flip flop you still need this one. You cannot ignore this because it's not positive or negative. No. If you don't put this, you don't know. Right? You want positive clock, negative clock, or you want the positive reset or the negative reset. So for the flip flop, you still need the list for the clock and reset. So yang ni sama. Q apostrophe 0, else equals 0. Yeah.
So apa yang kita combination yang itu Y2 Y ya. Untuk combination.
You should be right. Kena right. Dalam Verilog, Y must be right. Bukan Y lah.
Sebab dia
inside the always block. Okay. If it's inside the always block, it should be rest. Okay, but remember we don't want to use rest. Okay, so when you write your RTL, you use logic. Okay, so it doesn't matter if inside the always block ke, luar ke, it's always going to be logic.
Okay, so ada implementation dia dengan rest kita pakai rest intensi dalam consider.
Ya, kalau rest if it's in the always block, dia mesti kena rest. Mesti rest. Kalau assign is data flow kan, data flow punya ni. Data flow punya method dia punya model. Okay, tapi kalau SystemVerilog, you use logic for both assign and always. Okay, so the top part there is 2-to-1 marks, right? It's a 1 bit 2-to-1 multiplexer, and down there is just a simple difference of. Okay, so let's draw the plot diagram. Okay, so it should be a very easy one. Okay, there's the top level plot diagram. Multiply your 2-to-1 multiplexer and then difference of. So the application. Later we have more complex examples. Okay, so this one just a warm up first. Okay, so marks 2, marks 2 here, marks 2, and it has so input AB and select. All this is one bit. Okay, so if you want to put AB select outside or inside, I think it doesn't really matter, but yeah, I mean, if it's like this, I think it's better to put it inside. Okay, because for example here, if in one here is a port of inverter, so I put it inside. So and here also the output is called 5. Because if you essentiate this block, okay, then the block essentiating this will be the signal meter. So I think it's better to have it inside. Okay, and this is block pun sama lah, we have the PQ right here. Block. It's an active low reset, right? It's a if reset part. So it's an active low reset, and then we have the bubble here. Okay, block reset, and then we have the D and Q. Okay, and this is called the DFM. Okay, the question? What? Right. Okay, this is just another example. If you make a state machine or a control unit, normally you have both the combinational and the sequential part, right? In your circuit. So gain is always off, no need sensitive list. Always FF, need to talk. Okay. So I think this is a good feature. Right? Good feature. So previously you need to analyze the code to know if the always block is it combination always block or sequential always block. Okay, you have to think of it. Right? In this case, you don't have to think about your sensitivity list. That's number one. And number two, if you see always com, it means it's a combination of block. Okay, if you see always FF, it's a sequential block. So straight away you can see in your program. Okay, you don't have to think about it's always add, and you need to check, oh, is it combinational or sequential? I don't know, right? So I think it's a nice feature. I like it. It's always com, always FF feature. Okay, compared to Verilog. Okay, so I think we are the last one here. Alright, so one more exercise, but let's try to understand what this is doing first. Okay, so we have this listing in the SystemVerilog coding of a parameterized end-to-end decoder. To realize a 2 to 4 decoder, this decoder is implemented as shown in this listing. So depth param is not used anymore, so this is how we define the parameter. Okay, hash parameter instead of depth param in Verilog. Okay, so no more depth param. I think this is also more intuitive. The depth param is for me is a bit strange. Syntax. This parameter here is more intuitive. Hash parameter. Okay. So module decoder end-to-end hash parameter n equals to 3, n equals to 8. Okay, n equals to 3, n equals to 8. And then we declare the input. So input enable, input A, output logic, okay, is an error in the book. I don't know if it's been fixed in the new book. Listing 17, 758. Dia dekat SystemVerilog. Bukan dekat tu. Okay. It might be in yang ada book 1 book 2 tak? Yang ada book 1 book 2 tak? Ada. Ada book 1 book 2. Ada. So this is the SystemVerilog basics. Seems to be I need the terus masuk dekat application. You have a whole book, right? Ada buku lama tak? There's a chapter on unit plus. Yang ni ada. Output rest kan? Yang buku lama ada. Ini buku 114. This one is book 3. Oh, inside the book 3. Okay, never mind. So yeah, I tengok yang buku lama pun it's not fixed 100%. The new book might be in book 2. It might be in the new book 2. Ada book 2 yang baru. Ada tak tuntut? SystemVerilog. Never mind. You don't need the book actually. I think the example is clear here. So this guy is supposed to be logic. If you use Flash here, I think it will work. Because and then you say this one developed as a SystemVerilog file. because remember the Verilog is the subset of SystemVerilog. So it should work as well. Okay, and then you see the function always form P equals to 1, apostrophe 1, so all 1. BA equals to not enable. Okay, so if enable equals to 1, it will be 0, 1 bit enable. BA is the A location. A location and A is size 3 bit. Okay, so A is size 3 bit, B is size 8 bit. Default, okay, the default size is 8 bit. So A can take a value from 0 to 7. Because it's 3 bit, 0 to 0 until 111. So you put in your value here. For example, if you put 3, 3 is 011, right? So if you put B011, 3, so B3 equals to enable bar. Okay, enable bar. So if enable is 1, B3 equals to 0. Okay, all the rest will be 1. All the B is 8 bit, so B is 8 bit or 1. Okay, except the one that we enable, which is number 3 or 8. Okay, so basically that's what happened there. And then this module, we instantiate. So instantiating this module, we have first decoder 2 to 4, input enable, input S, output Z. Okay, and then when we use it, decoder N to M hash N24, so N24 is here. And so we override it. So this N here we override as 2, and M here we override as 4. And then this is the name of the instance, and then dot enable. So dot enable here is this one. Connect to logic 1. A here connected to S and B connected to Z. Okay, so let's try and do this. Okay, describe the operation of the module. What does it do? For the decoder 3 to 8, what is the output B when A equals to 3 and A equals to 5? What is the output B? And then create a new module 4 to 16 decoder, instantiate using a simplified port interface. Okay, so this one is a little bit tricky compared to the first 3 examples there. Okay, this one is a bit tricky. I have to think a bit what to do. Okay, so that's 10 minutes. 10 minutes, then we get the solution. Alright. So can you describe the operation? Just now I think I just described briefly what it means, but can you describe it yourself? So you see what the operation is doing. Possibly. Okay, so let's discuss the solution. Okay. Okay, so describe the operation of the decoder N2M module. I can say that the decoder N2M module is okay, you can say that. Simply you can say that bit B, B, A equals to 0. And others equals to 1, right? Bit BA equals to 0, and others BX or something here equals to for X not equals to 100. For X not equals to 100. Something like this, ataupun yang SJ in some way formulate, tapi something like this. Maybe kalau panjang sikit, jadi decoder N to M is an N to M decoder where panjang sikit lah encoder and encoder where bit 3 equals to 0 and this b equals to 1 where x is factor. Okay, and then so example a equals to 3, so your b is equals to so this is bit 3, so let's silap. So kalau bit 3 dia start from bit 7, 7, 6, 5, 4, 3, 2, 1, 0. 1, 2, 3. Okay, so not 3 from not 3 from here, 3 from here. Okay, and then you have b equals to 5, 3, 7, 6, 5, 4, 3, 2, 1, 0. 7, 6, 5. Okay, the fifth bit will be 0, the other will be 1. Okay, and then for the module, encoder 4 to 16. Okay, we have the input enable. But you can remove it, right? Yeah, I think you can get another one. Kita letak ni. Okay. Input. Okay, so the input now you have to change into if I want to use a 65 port connection. And then you have the output. Kalau output you can put logic. Kalau tak nak tak logic pun boleh. Okay, kat sini tak logic, but you can put logic. The input normally don't need logic. Okay, unless you want to put some value to the input inside the module, but normally no lah. Okay, and here is 4-bit, 16-bit, so it should be 15, 0. And it should match the pin there, it should be. Okay, 4-bit. And then when you instantiate the thing, you just go to the encoder and the name of the module. Diameter first. Diameter will be 4, 16. Okay, and then the name of the module for the encoder. Okay, and then you can do dot star. Okay, but is it correct? You have to be careful. If you do like this, it's not according to the spec. The spec there, they want to have the enable constant equals to 1. So if you do like this, maybe you lose maybe marks lah. I think they're like that 100% correct. It is correct, right? So apa silap dia? Here, if you do like this, I mean, you just mention fast load. Okay, but here it says that you want to make the encoder to be one constant. Okay. So you have to mix up, okay? You have to mix, so you have to dot star, comma, dot enable, 1. Okay? Kalau ikut contoh yang the previous slide macam boleh kan? Oh, tak boleh. Okay, dot. Boleh try nanti dalam assignment. Boleh try. In the assignment you have to write you have to do some association like this. Okay, you can do experiment. Okay, boleh tak I buat macam ni? Contoh contoh I buat 460. Can I do this? I never try myself. Okay, because the standard is always you do dot n like this. Alright, so there's no purpose to try like this. So maybe it works, maybe it doesn't work. Okay, I believe it's tool dependent, depending on the tool. Right? Maybe ada tool yang lebih relax, dia bagi. Okay, maybe ada tool yang tak bagi. Alright, tapi if you do like this, for sure it will work. If you do like this, for sure it will work. Okay, or check. Tadi backup maybe letak satu kat sini. Boleh. So dia tak tahu port mana. I don't think because kan. Port terakhir mungkin juga, tapi port terakhir B kan. So tapi kalau nak port depan, circle kat depan dulu. So I think to be safe, kan, just put here more safe. Okay. Kalau kita nak constant satu, then you can just do dot star lah. Here there's a requirement that must be 1, jadi the dot star will be important. Okay. Alright. So any questions? Alright. Okay. Okay. So I think we'll take a break. So we come back since we don't go to lunch. Okay. So can we come back at 2? Boleh. Can we come back at 2 p.m.? So we will complete the next part, the test drive. So tomorrow maybe we can go half day. Okay, so tomorrow we finish around 1 or 1:30 and then online. So online tomorrow just half day. So petang we can relax lah. So we finish everything today. I mean not everything. 3/4 of the course today. So tomorrow we can finish it. Okay, so in the meantime, in the meantime, good afternoon. We're going to do this. So just think about what is the difference between Verilog and SystemVerilog. Okay, and then you can share the information. Okay, so later you can log in to the panel. Okay, with a Google account, and then for example, you know the always scope. Verilog using always and sensitivity list. SystemVerilog using always scope. Contoh, ada banyak lagi. So maybe something interesting, maybe you boleh Google tanya ChatGPT. Some interesting difference. Okay, between Verilog and SystemVerilog that we can share with the other with everyone with us. Okay, so this one we'll do in the afternoon before we start the test session. Okay, so kita rehat dulu and then around 2 p.m. we'll come back.